So with the eliminations, they are effectively the same as your substitutions. So an SN1 gets you the same general result as your E1. An SN2 gets you the same general result as your E2 as far as kind of the characteristics of those reactions. It's not perfect. The biggest case being when you look at your products, your substrate, you're always looking at a stable product, okay, no matter what, for your eliminations. Which means when we look at the patterns for what reactions we expect to see, we don't see primary reacting faster like we do with an SN2, because that doesn't generate a stable product. We see the tertiary react the fastest, period, okay, for both the E1 and the E2, because it generates a better product. Okay? Your solvent in the E2 isn't all important, and that's because you really need that strong base. So they'll use pretty much whatever solvent you can to get that strong base into that solution. And the E1, we still want that polar protic solvent because the most important aspect in our E1 is that carbocation. We're going to do whatever we can do to make sure that cation is as stable as possible. Okay. Your stereochemistry, both of these will favor the trans, and that's where this can become a little bit tricky. Your E2, just like the SN2, happens in one step, which means the leaving group and the hydrogen that is getting pulled off by the base have to be on opposite sides of that double bond, okay, or the forming double bond, which gets you what's known as the anti-periplanar alignment. Okay? That is going to force your cis or trans stereochemistry. So you're going to have to make sure that your structure is drawn in such a way that those two groups are opposite each other around the double bond. Once that occurs, since it happens all in one step, everything else is now locked into position. If it's wedged in that conformation, then it's going to stay wedged as well as the other side. Okay? So you get locked in that position. You can't shift out of it. So you can get the cis in the E2s. Because the cis is a higher energy than the trans, those will typically require more energy put into it, maybe a little bit more heat to help force you into that position because it's not a stable position for it to be in. The Newman projection would be bad. Okay. Regiochemistry, you almost always get Zaitsevs. Very rarely do you see the Hoffman elimination. For the Hoffman elimination to really work, you need a tertiary halide, so a tertiary leaving group, and a sterically blocked base. So if you see a big bulky base, you might make sure that you don't have the Hoffman product as a possibility. Okay? So be aware that the Hoffman can show up in those cases. That bulky base can really mess with the end result. Okay? Oh, this was fun. So addition reactions, you get all sorts of functional groups doing this. You got your alkenes, your alkynes, carbonyls, and officially your imines as well. All of these are doing addition reactions. The alkenes and the alkynes react differently from the carbonyls and the imines. Okay? Alkenes and alkynes will get you a very particular chemistry, while the carbonyls do a different one. Why? They're all double bonds.
Alkenes and alkynes are liquid for half electron density, so you have to add something.
Carbonyls still have electron density. I don't quite accept that. I know where you're going with that, but
Heteroatoms?
why do the heteroatoms change it? It has to do with electronegativity. When we look at the alkene, and resonance really pushes it, the alkene, that pi bond is shared equally between both carbons. There is no favoring of one side or the other, which means both carbons are equally nucleophilic and equally electrophilic. Because the electrons are there, effectively your alkenes will only act as nucleophiles. Okay? So they will react with electrophiles. Electrophiles, or what's another positively charged species? Acids. When we get to our carbonyls and imines, okay, we mentioned electronegativity and resonance. What happens? Oxygen is more electronegative than carbon. The structure that we end up with is this guy. The electrons are not being equally shared back and forth between these. That means when we look at the reactivity for our carbonyls and our imines, that we see this imbalance. That imbalance is going to force certain chemistries. Our oxygen and our nitrogen are both electronegative, so they will both want to hold on to their electrons, which means the reactivity on that oxygen or nitrogen side of it is fairly limited. They aren't going to want to act as nucleophiles because they don't really want to share their electrons. We can make them act as bases on that side, but again, we're kind of forcing them to act as bases. Okay? We're forcing them to act as bases by adding strong acids. If we add a weak acid, says F that, I'm not reacting. It really needs to be something really strong and concentrated to help push that along. Okay? Whereas our carbon, on the other hand, is missing electrons, so it becomes a really good electrophile, allowing it to react with nucleophiles. Would it react with a base? For it to act as a Bronsted base, what does it need to do? Accept a hydrogen. Can it accept a hydrogen? No. Okay, so really when we're looking at our carbonyls and imines, they do react under addition reactions. But those addition reactions are where our carbon is acting as an electrophile. So we are always adding a nucleophile to it. The acid that we might add is to help polarize that bond to make that electrophile more electrophilic. Okay? So we get some slightly different chemistry between these, and that's because that pi bond is polarized due to that electronegative element. Kind of makes sense? So with our alkenes and alkynes, give it an electrophile, give it an acid, push it and see what happens. Okay? Works pretty well in all of those cases. So if we go through and take a look at the reactions for our alkenes, you'll notice that in all of these cases, that's what we're doing. We're giving it a positively charged atom in some form or another. Okay? Starting with HX going counterclockwise. HX, acid. H3O plus, acid. Next one, H plus, acid. Next one, BH3. What's our positive atom in BH3? Boron. It's the empty p orbital in boron. We're reacting it with an electrophile. Our alkene's reacting with the electrophile. Okay? What's the next one? Mercury. That one's a bit weird. Mercury is just odd altogether. Okay? For those of you that remember carbines, mercury is effectively a carbene. It has a positive charge by losing an acetate, but it also has a lone pair. So it acts as both a nucleophile and an electrophile. So the alkene can attack the mercury, kicking out the acetate, but then the mercury can share its electron density back to form the mercuronium ion, and that's that triangle. Okay.
Does BH3 give us the Zaitsev or not the other one?
So Zaitsev versus, or it's Markovnikov versus not Markovnikov addition reactions. So Zaitsev's is the other direction. I intentionally don't memorize that or even look at it because I don't think it's as broadly applicable. Markovnikov additions say hydrogen goes where there's more hydrogens. Well, in the case of BH3, what's your positive atom? Boron. You can't apply Markovnikov because you're not putting a positive hydrogen on the structure. Okay? Where Markovnikov's rule works is when we're looking at acids, because our hydrogen is positive. So if we go through and look at all of our acid applications, the hydrogen goes where there's more hydrogens, the least substituted. Where boron is our positive atom, where does the boron go? The exact same location that our positive hydrogens went.
Well, my question is,
Why do we see a different result at the end of it? BH3 does put on a hydrogen. Does it put on hydrogen ion? It puts on hydride. It's putting on a negative hydrogen. So when we looked at the Markovnikov rule, he's talking about putting on hydrogen ions as that positive. As soon as we switch to BH3, it's now no longer a hydrogen ion, it's hydride that's getting added. It gets added the exact same way a negative atom gets added in all of the acid catalyzed reactions. It's just getting added in a slightly different position, but now it looks like hydrogen, so we all panic and say, oh, it's the opposite. It's not the opposite, it's doing the exact same chemistry. The nucleophilic electrons in the pi bond go to the positive atom, period, every single time. There is no variation. Okay? After that, we have to give some electrons back to the carbocation on the most substituted position in our alkene. So that's why I don't like referring it to the Markovnikov rules. It's a valid observation, but then you have to remember not just when it's true, but also when it's false. And that, to me, is problematic. All right, that's two things to memorize, not one. Does that kind of make sense?
So now that leaves me with just memorizing that BH3 will do that. Because does it do that because it's, bulky or some reason like that?
The reason BH3 goes to the least substituted position has to do with our alkene. Where do the electrons in that pi bond spend most of their time? We have two options. We can put the negative charge up here and the positive here, or we can put the negative charge, let me try that again. Or we can put our positive charge here and our negative charge down here. Which is better, orange or red? Orange, why?
Because negative on the tertiary is a bad thing.
Negative on the tertiary is a bad thing, or we could say positive on a secondary is a bad thing. So if we follow the chemistry, we don't need to memorize some stupid, he was probably very intelligent, person's name. Okay? What we can evaluate is the chemistry and leave the names out of it. Okay? So that's why I don't like using those. Okay? The chemistry is still true. If you've got that rule memorized, that works. You can memorize Markovnikov and anti-Markovnikov and go through for each and every single one of these reactions and say, this one's Markovnikov, this one's anti. But it's not then just memorizing that it's Markovnikov. What was Markovnikov's rule? So really, you got three things to memorize. And that's for each of these reactions.
And then you have to memorize enzymes in addition.
And yeah, so to me, it's not worth the effort. Okay. I would rather understand why that chemistry is occurring than going through and looking at it. For the alkenes, alkynes, I think for the alcohols as well. Remember, I've got all of these spider web things online. I also have the Word document that lists the reagents, the functional groups. Is it anti? Is it what type of addition is it if it's an addition reaction? Anti versus syn. Is it a Markovnikov? Is it anti-Markovnikov? I've got all of that written down for a lot of these functional groups. Okay. They aren't comprehensive lists of the chemicals and reagents, but they're at least a good first pass. Okay. Within these, since you mentioned your anti versus syn addition, that again comes from the mechanism on how each of these things occur. When we look at the BH3, we end up seeing this as a syn addition. The hydrogen that gets added and the OH are added on the same side. And that just comes from how those reagents work. The boron and the hydrogen initially get put on the same side. The peroxide comes in and kicks the boron off in that exact same position. So we still get a syn addition. Syn additions tend to be a lot more difficult to do because you have to do everything all in that exact same space. There's so much electron density in there that becomes a little more dicey. So typically your syns are a little bit less frequent because of that. Okay? If we look at the mercuronium, none of those structures are good ones to actually show because you can't see syn versus anti on those because of where your OH went. But those end up being, those will be anti. Okay? And again, it comes from how do you put all of those groups on there. And that comes ultimately from the mechanism. Okay? The reason why you typically see the mercury, you'll notice if we take a look at the mercury product versus the H3O product, what's the difference? Absolutely nothing. So why would we bother to use mercury, which is highly toxic?
Probably not.
Has to do actually with the mechanism. I used to think it was there's no reason I would use it as that. I'm not going to risk my life. Okay. What happens in the mercury? No carbocation. You get the mercuronium ion. There's no carbocation, which means no rearrangement. With the acid, you get a carbocation, you can get a rearrangement. It doesn't always happen, but you can do the rearrangement. So it again comes back to understanding those mechanisms. Kind of doubt that you'd see that kind of nuance of it, but synthetically that's what you'd be thinking. Okay. Your bromine additions, I would treat bromine like I would mercury. It's the same general idea because you form that mercuronium ion, you form the bromonium ion, followed by a nucleophile. Nucleophile in the first case shown was an alcohol, so we get OR. The nucleophile in the next case was water, so we get OH. Nucleophile in the next case, it's the other half of the bromine. It's the bromide, so we end up seeing that bromide get put on.
Does that work for all halogens?
Yes,
Okay.
which is interesting because I show X all the way through it, but I don't show X for the bromines. I don't know why that's the case. But yeah, that will work for all of your halogens.
Chlorine and iodine.
Yeah. Bromine is typically more often used just because its chemistry is a little bit more controllable. Okay. The iodine, I think, tends to happen very slowly. The chlorine happens faster, so you could potentially get radical reactions happening, and you don't want the radical reactions. Fluorine is never used because fluorine, as far as radical reactions go, is ridiculously fast to the point that it's explosive. Okay, so they just don't use fluorine. If you want to put fluorine on, you have to use. We talked about that in one of the chapters. I don't even remember which chapter it was. You could put on fluorine if you really, really wanted, but it's coming on in a different form of a reagent. Okay. What the heck? Yeah. This one's, because I used HBr. So if we use HBr, that will react with the alkene to put on hydrogen and bromine. You'll notice, where's the bromine? It's at the least substituted. We might even go as far to call this our anti-Markovnikov. But it again has to do with how the mechanism works. Okay? The result is you form the bromide radical. The bromide radical reacts with the alkene to neutralize the radical. Where's the more stable? And because it's a bromide radical reacting with a neutral species, we end with a radical. Where's the radical going to form on our alkene? The most stable, which ends up being the tertiary. That tertiary radical can now react with a hydrogen to put the hydrogen on. Okay? So your radicals tend to give you kind of the opposite result of what you would have expected for that reagent, okay, because of how they function. One that's not in here is if we had reacted that, whoops, that's an eraser. If we'd done Br2 with our radical initiator, what would our product be? This one's a bit obnoxious. We could put a bromine over here. Sorry, I'll answer your question in just a second. Or a bromine, and I'm going to put it as a dot as an option, or a bromine over here. Okay. Why did the bromine not react with the pi bond? Allylic position. We're looking at activating that allylic position. We could do it with Br2 in light. BR2 is in such high concentrations that we would probably see the bromine adding across the double bond. If we really wanted to make sure we got the allylic position to react, instead of saying BR2, we'd see NBS.
So NES, BR2, same thing?
Effectively the same thing. It just comes down to a concentration difference. NBS gives you such a small amount that you can do reactions that you wouldn't expect. Okay? A little bit more kinetic reactions than thermodynamic. Whereas BR2, it's in there in such a large amount that we're going to try and neutralize that as fast as possible. We get the pi bond reacting. Okay. The last one is looking at hydrogen with any one of your catalysts to add hydrogen across that double bond. Okay. Your alkynes, because I don't think that's on my next slide. Oh, look at that. Alkynes are effectively the exact same thing. Okay. There are a few kind of odd exceptions. The big one is when you're adding on, whoops, go away. When you react it with your H3O plus or H plus and H2O, we still get, whoops, the same general idea as we got with our alkene. Water comes in to attack. I'm going to remove a hydrogen from water right away, just because I don't feel like drawing that last mechanistic step. Look at that. What functional group is that? It is an enol. What's the issue with enols?
It's not incredibly stable.
It's not stable, and it tautomerizes to give you the ketone.
That's one of the questions in here.
Right. So that chemistry, it's the exact same as our alkene. It looks dramatically different because they're adding this extra tautomerization. I would highly expect to see that on the ACS test because that brings in ultimately first semester material, the alkyne reactivity, with second semester, do you understand what's going on with the enol? Okay? So I would fully expect to see that. So it could show up in a synthesis. It could show up just as in, here's an alkyne with this reagent. What happens? What's the product? I would guess as possible answers for this, they would give you this guy, and I would probably anticipate seeing this as well.
What's the question?
What react? So the alkyne with H2O and acid.
What's the major product?
What's the major product?
It doesn't give you the enol.
Oh, that's interesting.
Yeah.
I would have expected that as a valid answer for
I
that.
would have thought so
Well,
too.
as a challenging ACS answer.
This one has HgSO4 underneath the arrow. What does that mean?
So typically with this, you would catalyze it. The alkyne, because you've kind of packed in all that pi electron density, is actually relatively stable. So we need something to help polarize it. Just like with the alkene, we did use something to polarize it, or we could. We use mercury. The alkyne does the same thing.
Okay.
It needs a mercury catalyst to help
But
push
it's
it.
not really a big step in okay.
No. It officially goes through the same mercuronium as the alkene goes through and does, but ultimately we don't care about that. It does the same chemistry. We put an OH and a hydrogen on our alkene, or on our alkyne with one of those pi bonds. The resulting structure rapidly tautomerizes to the ketone.
Okay.
Right. Could we make an aldehyde?
That's one of the answers.
To make an aldehyde, where would the OH have to go?
At the end.
Has to go at the end, which means where do we put the hydrogen? At the least or the most substituted position, which is anti-Markovnikov. Is it possible to put a hydrogen in an OH anti-Markovnikov? Is it possible to put a hydrogen in an OH anti-Markovnikov?
Yeah.
So we could react our alkyne with that exact same setup and get the aldehyde because we get that anti-Markov-Markov result. Okay, so it's the same chemistry again. We're reacting the pi bond. Pi bond does its thing. Now it goes, oh crap, I've got two functional groups next to each other. I need to fix this. And it fixes it by turning it over into the ketone.
Is
Yeah.
that the terminal versus whatever alkyne?
It would have to be terminal to get the aldehyde because the aldehyde is at the end of a carbon chain. Okay? So all terminal means is that it's at the end and we have that hydrogen. To get the aldehyde, we'd have to have that terminal. Okay? Really the reason why we talk about terminal versus internal is the secondary chemistry with our alkynes, that we have an acidic hydrogen. So what we can do, and I gotta be careful, this is a typo on my part. This is not true. You can't do that. We'll talk about that in a second. We can use a strong base to remove that hydrogen, and what we end up with is now a strong nucleophile. That nucleophile can then attack something. Usually where I've seen this is they do it twice so that you can chain grow outside of the alkyne, so it goes both directions. Very rarely have I seen it only being a terminal alkyne. It's usually acetylene that you start with.
So it would be not two sides, both sides.
So it would be both sides. Would both sides be deprotonated at once? No, why not? Too much electron density in that same spot. So we do one, then we'd have to follow with the other.
That's a little bit to the one about the acid in water on the alkyne.
Okay.
Why did, and maybe if we just talk this through, it'll be apparent to me, why does it stop at a pipe, or, at just the double bond? Why didn't?
So what we have to look at is the reactivity of that double bond. So if we draw that again real quickly, what we're looking at was this.
Yeah.
Okay. We have two functional groups here, an alkene
And alcohol.
and an alcohol. Before we can say we're good, we have to evaluate, is there something I can do to kind of balance those two functional groups out? And yes, I can. I can tautomerize that into that. Okay, and that's what I think it was 22 that was talking about. This is an equilibrium reaction that greatly favors the carbonyl.
I don't know, I was thinking it would reduce it even further so that there'd be.
So, well, that's why the very last answer I put on there was the two alcohols. That is, a reasonable thought. We say alkenes react the same, or alkynes react the same as alkenes. But before it can react, that second pi bond can react, it must kind of assimilate itself and say, I've fixed this alkene alcohol issue. And it hasn't. It has to propagate further across. Now we're at the carbonyl. Carbonyl says, no, I'm not going to react with an acid. There's nothing to stabilize me.
Okay, I get it. That makes sense. What were you gonna say about the sodium and the ammonia?
Yeah, that's what I was going to add here. The sodium and the ammonia, I am going to kind of say that you should check this to verify on me because I'm not positive. I shouldn't completely do that. Try that again. We did talk about it, and I definitely talked about it wrong because I said you could use it synonymously, and that's technically wrong. The sodium will give up an electron, so what we can do is have it give up an electron to the pi bond. Okay? And what will end up happening is that we can reduce the pi bond to an alkene. So it'll stop at the alkene and not propagate all the way to the alkyne or the alkane. So it's kind of a nice reagent in that respect. If we have the alkene, we can get to the alkene, or if we can get our alkyne, we can turn that into our alkene relatively easily, okay, without having to go all the way down to the alkane. The part that you need to check on is if we make this an R group out here, do you generate the cis or trans product? And I don't remember that.
Or could it be both?
You get one or the other. So there's really two primary reducing agents to get the alkene. This is one of them. The other reducing agent is H2 and Lindlar's catalyst. Both of those reagents will stall at the alkene. One of them gives you trans, one of them gives you cis.
It says that that's trans and Lindlar's would give you cis.
Man, so I got it backwards. So the sodium in ammonia was trans, and Lindlar's is cis. Right, so the Lindlar's one is probably the more important one to remember in my book, because that gets you the disfavored alkene product. Okay, because trans gets you more space, so I'd remember the Lindlar's.
Radical mechanism.
The sodium in ammonia is radical. Lindlar's is radical?
No.
Yeah, Lindlar's is platinum.
Yeah, it's weird.
Yeah. The sodium one is definitely a radical mechanism. Okay. So,
I remember that Lindlar's one, how they described it, where like you have the hydrogen sticking out of this thing that they called like a plate. So the
Yep.
hydrogen's immediately attached to the pipe bond like that, and that's how you got your cis. 'Cause it forces the
Yeah.
platinum that or something like that.
I should have remembered that too. Awful teacher.
Hardly. I don't remember any other teachers feeding me pizza.
Oh, that's all I gotta do. So this slide is what we've already, or this last section is what we just talked about. A reagent that turns an alkene into an alcohol will turn the alkyne into the carbonyl. So your boron and your mercury will do the same thing. What's your
It said that NaH2 and H3 liquid turns the terminal alkyne into carbanion.
Yep. Yeah, which is exactly what we did. So if we go back one step, come on, or no, that was the wrong thing. So if we go back one step, NaNH2 is a base. Pull off the hydrogen, and we've got the carbanion. Okay, so there's our alkynes.
There you go.
That's rainy nickel. Does rainy nickel do the same thing? Well, we already talked about it, so we'll just leave it that I was right when we talked about it. So our alcohols, you can see alcohols show up in a variety of different places. A lot of them are from your alkenes. Alkenes are pretty synthetically useful. You can just get a lot of different directions you can go with your alkenes. Okay, so when we're going to try and synthesize our alcohols, you got substitutions, additions, reductions. Okay, so all sorts of fun little reagents that pop in and out of there. Okay. So yeah, you should be familiar with those reagents. Within those webs, I do want to point this out because I've noticed with the carbonyl one that we definitely had some conditions that were missing or people not seeing. I am showing branches. You need to be very careful with those reagents. In one branch, the first one up there, we've got a nucleophile. In the second one, I have a nucleophile as well. Yet if we look at the results, they're very different. Okay? So make sure that you look to see what those conditions are. In our first case, to get a strong nucleophile, we're probably running under basic conditions. With the weak nucleophile, what did we have to do to get that reaction to work? You had to run under acidic conditions. Okay, so a lot of the reactions that we've gone through and looked at have acid-base steps in them. Those acid-base steps can affect how the rest of the reaction would actually occur. So if you're going to look at the webs, make sure you're very careful with what those reagents mean. Okay, primarily as it's concerned about basic and acidic conditions. That was a silly step. Reactions of alcohols. Your alcohol has a lot of chemistry. We've got a relatively acidic hydrogen off of that OH. we have a basic oxygen, and we have an electrophilic carbon. So there's lots of little places where that thing can go. We can either have it act as a base or a nucleophile, have it act as an acid, or have it act as an electrophile. So lots of little chemistries that you're going to have to watch out for. In almost all cases, you're doing probably multiple versions. So if we look at, let's see. No, never mind. I was hoping I could see one that was obvious. I don't see any that are obvious. So in this case, we've got both a synthesis and a reaction. So the top portion of this is our synthesis of our alcohols. The bottom portion is our reactions of alcohols, to try and get a little bit of everything. Okay. So this is, I guess the last slide was alcohols too, wasn't it? No, this was reactions of alkenes. In this case, the reactions of those alkenes all resulted in alcohols. Okay, so it does, you do see a lot of overlap between these. Here we're looking primarily at the formation of our alcohols, not always from alkenes. We're also looking at some of the reactions of our alcohols. In most cases, we're looking at activating them to do something else first. Okay, your alcohol, your OH, is a pretty horrible leaving group, so it won't leave directly on its own, so we have to facilitate it some way or another. Okay. So in the case of the SOCl2, we converted it into the good leaving group of ultimately SO2. So we took that part out of it. In the case of reacting it to get our alkenes or our substitution, we first had to react it with sulfuric acid as a catalyst to activate the alcohol, turn it into a good leaving group. Okay, so almost all of our alcohol chemistry is based around making that leaving group. Okay?
So
Yes, sorry.
when you say no different stereochemistries, meaning what they're
MCPBA, so if we look at, it's really two branches, so we'll call it a red branch and a blue branch. So our red branch versus our blue branch generate different stereochemistries, but I was trying to condense it all in one thing. The red branch, through MCPBA, what is the stereochemistry of those alcohols? You guys remember that? MCPBA makes the epoxide, then our water comes in, does a backside attack. What's the relationship between those two oxygens? Opposite sides. They're trans. Okay. When we take a look at the OSO4, that comes in on the same side, we get a syn relationship, or cis. Sorry, I couldn't think of what it was. A cis relationship of those alcohols, or it would be a syn addition. Okay? So that's what it's saying by different stereochemistries. I just didn't feel like drawing it again.
No, that was good. The potassium permanganate, cold and dilute, now we've seen
Mhm.
potassium permanganate.
The permasa, oh, because I did have that on there. I did show the ore.
Seen it in different places throughout the semester, at
Yep.
different temperatures.
Potassium permanganate is a really good oxidizing agent. Okay, and that's exactly what's happening here. We're putting oxygens onto that structure. If we keep it cold and dilute, we can minimize that oxidation a little bit. Okay. If we heat that up, it fully cleaves the alkene and splits it, the ring open, and we get two halves. Okay, and then we fully oxidize both of those positions. Permanganate, since it is a good oxidizing agent, can react with a variety of different species under the right conditions to fully oxidize. So you can push it to ketones. You probably wouldn't see it stall out in an aldehyde because the aldehyde still has that oxidizable hydrogen. So if you had an aldehyde in the presence of permanganate, you would probably push the carboxylic acid. Okay. So it's kind of the workhorse of oxidations. The other oxidizing reagent on the far right there, showing PCC. Really, we'd have to look at the oxidation supplement. Remember how I've been talking about it? PCC is politically correct chromic acid, so it's just a milder oxidizing agent. All right, nobody seems to remember that, but I think it's cute and it works.
That totally.
You guys remember it? Oh, okay, cool. Did you get the answer right?
No,
Okay, then that doesn't help.
sorry.
Ask the question.
Yeah. So it doesn't oxidize as far. So if you want an aldehyde, PCC is what you want. If you want a carboxylic acid, it's got to be chromic acid or permanganate. Okay. Just because those will fully oxidize, the PCC won't. If you want to stop at a ketone, pretty much any oxidizing agent is going to do that, because the ketone only has one oxidizable hydrogen. We can get away with any oxidizing agent because there's only one position that it can oxidize. After that, it's done for. Okay. Oh, I had to throw in epoxides again. So with your epoxides, I think I threw this in because I saw some weaknesses with this. If you've got a strong nucleophile,
You could go to the least substituted side.
what you're getting is what I would reference as an SN2 type reaction. So I'd even put it in quotes. It is still a substitution. It's just kind of a weird substitution because your leaving group doesn't leave the structure. It just leaves the carbon. Okay. And if you have that strong nucleophile, that's what's going to happen. You're going to get your leaving group to be pushed off by your nucleophile. Well, for it to be pushed off, the nucleophile must get access to the backside of that bond. The only way it can get access is if it's sterically unhindered. So if we take a look at that epoxide that we started with here, one of those was technically a quaternary carbon, and the other one was secondary-ish. Right, the secondary is less blocked. That's where our substitution is going to occur. The next two reagents, or the next one, shows again our strong nucleophile, our SN2, but now we can see the stereochemistry a little bit better. Okay? We still get the nucleophile coming in doing backside attack. Our oxygen is going to be wedged upwards. The nucleophile had to do backside attack, so it has to be dashed. It has to be going away. Okay? One thing that we could add on this, because I've noticed that this does confuse people, if I put in another dash here, and let's call it, I don't know, isopropyl. Okay. Don't want to call it that. I'm going to have to call it a methyl. Kind of the natural response is that when we draw, we're coming in and attacking that carbon. Okay? And yes, in this case, the carbons are both the same. Ideally, you don't show the arrow attacking there, because that sure looks like it's coming in right next to the oxygen, which if you were going to try and draw the product, you might very well show the nucleophile as a wedge, which it can't be. It has to be coming in from the backside, which is all the way over here, which does what to that dashed purple bond? It causes it to flip upwards to becoming the wedged. Okay? Which isn't the easiest thing to see unless your arrows happen to be drawn absolutely perfectly or you're super comfortable with the three-dimensional structures. Okay? So kind of be aware of the limitations of your arrow pushing and make sure you've got those alignments proper. In the last case, well, actually even before we do that, when we're running with a strong nucleophile, what conditions are we likely looking at? Not to color code or anything, but yes. We're looking at basic conditions. What happens if we now shift it to now where we're looking at acidic conditions?
A weak nucleophile and he needs his friends, so he goes to the most substituted carbon, where his friends are.
Our oxygen gets pre-activated by the acid, and we now have a really good leaving group.
I thought it
Okay.
already happened.
Yeah, this is a pretty bad one to show. Let's cross this out, make this a nucleophile. Okay. And it can be a weak nucleophile. Now the question is, where does the nucleophile attack?
The weak one goes to the most substituted.
Why does it go to the most substituted?
Because it means it spreads.
It's like the SN1 kind of.
We're running under SN1 type conditions here. It really does push that SN1 type. And we really got to say SN1 type, because I don't think it really pushes 2 steps. Okay, the epoxide kind of forces that to keep kind of tight. Your nucleophile is going to come in still backside attack, which is why it's hard to call it SN1 strictly, because it's still a backside attack. Okay, but where is it backside attacking? The most substituted position. So our nucleophile ends up coming in on the backside, and that's our end result. Okay, that doesn't look any better. It looks better on my screen. Okay?
Does it say nuke?
It says nuke, yeah. So those two, again, even in this reaction, what's the relationship between the nucleophile and the oxygen? They're still on opposite sides. They're still trans. It's still an anti-addition. Okay. Yeah, and it's a little bit weird to think of it as an addition reaction, but really it is. We started with an alkene, made it the epoxy, and we still had sort of an alkene, 2 bonds to an oxygen, and we ended up adding across that.
As far as the ACS test, would we need to know names?
Like Markovnikov, Zaitsev's.
Yeah.
They do ask those every so often, yes.
Like I came across a question with the, that was, the sapling one where it said, okay, which one of these reagents reduces something like a ketone? And it gave you all the names of all the, I don't remember what these
So
names mean.
names of reagents, to a lesser extent, yes, they do ask for that, but not as much. They usually give you the structure.
And I said reagents, and that's not really what I meant, but reactions like the very failure, reduction.
Usually very rare. Very rare to see that. The results of reactions, that's a different story. So Markovnikov, Zaitsev's, Hoffman, you will see them make reference to those names. For the name of the reaction type, like Wolff-Kitchener reduction, your Bear-Villiger, those names, probably not.
I don't know. You do a heck of a job pronouncing them. I mean,
Well, in all honesty, do you know how to pronounce them?
No, not.
So I can make up whatever I want. As long as I'm consistent, it doesn't matter.
Good job.
So our aromatic compounds, when we moved into chapter 18, we really just had nomenclature, which we already talked about Monday. But then we've got aromatic and anti-aromatic and officially non-aromatic as our definitions. You will need to keep those straight. You will be asked questions about those because those are very second semester based questions. Okay? Very rarely does anybody talk about your benzenes in first semester. Okay? So because of that, they are full. That you should fully expect to see those. Okay? So what makes a structure aromatic? You need to know those rules. Okay? So you're looking for your overlapping p orbitals, and then aromatic is 4n plus 2 pi electrons. Your anti-aromatic, same rules except 4n pi electrons. Okay? One option, instead of remembering that formula, is you could remember the pi electrons. So 4, 6, 10, 14 for your aromatic. After 14, I mean, the pattern does continue. I doubt that they'll show any out there.
It's 2.
I can't count.
The ones with the NHs piss me off. They.
Yeah, you will still be responsible for those heteroatoms, deciding on when you can count those pi electrons. If it is an sp3 atom, count a single pi electron, or count a single lone pair electron. Right? I think that's the easiest way to remember to count those pi electrons, or count them as pi electrons. If it is not an sp3 atom, you cannot count the lone pair.
Not sp3.
Can't
And
count.
then sp2s, like say there's one NH and then one ANH at the bottom, and then it has pi electrons next to it, both of them. Only one of those.
If the nitrogen is not sp3, you cannot count the lone pair. It has to be sp3 hybridized to count the lone pair.
Can't count that.
So
Okay.
I think, so I've got this one. So pyridine is aromatic. It has 6 pi electrons. We don't count the nitrogen, the lone pair on that nitrogen, because what's its hybridization? It's sp2.
And it already has electrons in the.
So it's already contributed electrons to the pi system. So we don't look at it. Okay. A question that I meant to ask on you guys but didn't. Let's try that. Aromatic or not?
2, 4.
No. Yes.
I don't know.
It's a tricky one. So what we're looking at
It's
is our
sp3.
pi electrons. So let's go through and show where all our pi electrons came from. So one, for our pi bond over here, there was 1 electron from each of those carbons. For our pi bond over here, 1 electron, 1 electron. How many pi electrons are in your aromatic system? Are in the pi, or in your ring? Remember, they all have to be in the ring. Yeah, I like your hand, Daniel. How many electrons are there?
I don't know.
It's only 5.
Can we do a
Resonance.
Doesn't matter if you can do resonance. This electron does not contribute to the pi system.
Okay. Because it's out. The pi bond is out of the ring.
Yeah. So it has 5 pi electrons.
Okay.
It has to be part of the ring. Okay. So I wouldn't be surprised if you saw something like that on the ACS test. Okay. They can throw on a whole bunch of extra things on the outside, and you go, oh yeah, I can throw that in there. No, you can't really.
And boron is funny because it can make 3 bonds, so it usually has 2 bonds and then a lone pair, so it can contribute.
Boron can make, so if we tried to draw the Lewis structure, so this is where it's nice to have your Lewis structure ability is really, really good and raring to go. Yeah, everybody laughs at that statement. Boron has how many valence electrons? Rhymes with ni. I couldn't come up with something. It only has 3 3 valence electrons. Hydrogen comes in with 1. There's 3 of them, so we get 6 total.
Oh, that's how you figured it out? I was trying to look at the periodic table. I can remember.
So what's the hybridization of the boron? That's the shape. What's the hybridization?
SP2.
sp2. So it has a leftover p orbital. So if we put boron into the structure, let's erase that for the moment. We made this boron. We do have overlapping p orbitals. Do we have the correct number of pi electrons?
No.
No,
Well, not with that electron.
not with that structure, no. All right. So we'd have to change our structure to go through and get the
I'm
boron.
confused. Can you draw it normal without the
I don't think I can actually with 6. We have to have a dot on one of them. So let's pick a different structure. Let's put 5 carbons, because maybe that'll be easier for you to see. So this has all of your overlapping p orbitals. That's set. But we don't have the correct number of pi electrons. So it would be anti-aromatic. If we wanted to get really obnoxious with this, How many pi electrons? 6. Boron, being sp2 hybridized, has a p orbital. It does have an empty p orbital. So I can push electrons through it, which makes it aromatic.
You
Right.
said that's boron's sp2?
sp2.
Yeah, then, wait, SP2, so we can
So
only use it if
we
it's
can only
SP3.
use pi electrons,
We don't
but
need
we don't
pi.
have pi electrons. In this case, it's an sp2 atom, and what we want is the vacancy. All we want is an empty orbital, and that's exactly what boron gives us. Okay? It would be the same as if we, how big is my eraser? If we'd made this just a carbocation, still aromatic.
What does a non-aromatic look like?
We can go to, oh, non-aromatic?
Yeah.
Oh, there we go. Non-aromatic.
That's true. Okay.
Pretty much every structure is non-aromatic.
Then either one of those things.
Yeah.
Okay.
And those are ultimately just rules, you just have to know them. After that, you're looking at your EAS summary. I didn't go through and summarize all the activating versus, actually I think I did. These are all of the reagents that you could go through and use. Remember, you can use them in conjunction with each other, and that's pretty much how you get to that second tier, the blue level. Everything else is a single step kind of deal. Okay? So you just need to kind of remember all of those pieces. We can get directing effects if we have more electrons than hydrogen. What does that mean? We're looking at an activator, which does what to the speed of the reaction? We get a faster rate. Where does the substitution occur? I would prefer it if you said para-ortho. Why? Steric blocks the ortho position. We favor the para position. Okay. I still say it the other way. If it has less, or it's less not willing to share electrons, what happens?
It's a deactivator.
It's a deactivator. And what you said was a very good point. Sometimes you'll see this as a withdrawing group. Usually electron withdrawing group, also written out as EWG. Conversely, with our activators, we can also see electron donating group, or EDG. Ultimately, they're saying the same thing. Okay. Deactivator does what to the rate of the reaction? Slows our rate. Way to get fancy with the decrease there.
Will deactivate, decrease.
Sorry, apparently I'm just a little too slow today. Where does it direct? And we get the meta direction. So that works for all atom X's except your halogens. Your halogens float in the middle of this. They are deactivators, so they will slow reactions.
Exception.
Yeah, it is definitely an exception. Slow reactions, but then direct to the para-ortho positions. Okay. And just in case she listens to it, this is what Lacey was asking about with bromine being donating versus withdrawing. Bromine has the electrons. It can stabilize the positive charge. Okay? And that we would see in what Jessica was asking about, sigma structures, or the sigma complexes. Okay? So you don't necessarily need to know all of that. What you'd need to know is what's up here on the slide. As soon as you got this stuff down, you don't need to know anything else.
They also asked in your question about why something affects where it directs or something like that, and it was, the options were about induction versus resonance. And I thought that was interesting, because
Yeah.
technically we think about them as inductive effect, but they're really resonant.
We do have that resonance ability. And so when we're looking at halogens, yes, we do have that kind of competing issue between resonance and induction. When we're thinking about our halogens in induction, think back to when we've referenced them. We reference inductive effects when we're looking at halogen effects on carboxylic acid functionalities. Are they more acidic or less acidic? Could we have looked at resonance in those circumstances? No. In all of those cases, we were linked with sigma structures. There was no ability to show resonance. Resonance should trump induction. Okay? So if you can draw resonance, do the resonance first, then if the resonance doesn't help you out, then you can think about induction. Okay? Other questions? This is fun stuff. We're now up to another 60 minutes, so I'm going to take another